database management, which is concurrency control. And this problem is very relevant and very well researched in many areas of computer science. In fact, in many aspects of engineering or many aspects of real life, whenever we have multiple processes or users or things that want to share some kind of shared resource. Whenever we have shared resource, multiple users trying to use that shared resource, we have this problem of concurrency. And you've seen it even in roads, for example. In the roads we use every day, they are not designed for one user at a time. We don't kind of book, I'm going to use Shamal Road today, and you make a booking, and you only use it by yourself. That's not how it works. We all, many people use it at the same time. So as long as everybody is taking their line, as long as they follow certain protocols and certain rules, it should be fine. Especially when everybody just going in their own lane. There is no problem. There is very unlikely problems. Of course, there is always chances of issues, but if people abide by the rules and they stick to their lanes, and when they want to, when it becomes problematic, when they want to share the same resource at the same time. I am in my lane and I want to change the other lane. I can't just go and change. There is a protocol I have to follow, and there are some rules I have to follow to avoid collision or to avoid unwanted state. So I have to check the mirror, then put my if the road is clear, put my indicator, and maybe check the blind spot in the last minute before I change. Okay. Then when it comes to intersection, also there are mechanisms and rules to allow that concurrent usage of the road without collisions. So mechanisms in this case, there are, what are the mechanisms? Traffic lights, and traffic lights have some rules. Like when it's red, you're supposed to stop, and then when it's green, you go ahead. So basically, when we have something shared, we cannot just go and use it, all users use it without any control. Otherwise, we are waiting for chaos and waiting for problems and waiting for issues. Exactly the same in a database world. We have a shared database, a shared resource, and we want users and applications concurrently use it. Now, if we don't do anything about it, then definitely this will create inconsistencies. Not like accidents and crashes, but different types of problems. And of course, for us to avoid these inconsistencies and to keep our database in a consistent state and our data safe and consistent, we have to have some mechanisms. The database management system needs to have a concurrency control manager that will control this concurrent usage of the database. Yes? So the good news here is so at the end of the day, the database at the end of the day, what it sees multiple transactions. At the end, it sees multiple transactions coming, and these transactions have different operations. Okay? So a transaction is nothing but a set of operations. The set could have one operation only. Somebody is reading or writing. Sometimes you have multiple things in the same transaction. Okay, so the concurrency control manager need to schedule and need to execute those queries in a way that there will be no conflict, no inconsistencies after the execution. Okay, so these inconsistencies, type of inconsistencies that could happen, we discussed them last time. Any of you remember some of the anomalies or some of the issues that can arise if we don't have any concurrency control, if we leave it open? any transaction can do anything. What could happen? Lost update. Thank you. One example is lost update. What does it mean? Some small scenario of a lost update. Sorry? The bank loses money, yes. Remember that example of we have two people sharing one account, and they both have, let's say, a card to withdraw from that account. This is a realistic example. In a shared account, you can have multiple accounts. And these accounts, you can take those cards and go and withdraw that money, okay? So if there is no concurrency control mechanism in place, what could happen is both of us, we go to the ATM and both of us insert our card. And let's say the way the withdrawal is done, as an example, we first read the balance. So we all both read the balance. And then what happens is one of us will withdraw some money, and then that amount withdrawn will be reduced from the balance, okay? So we both at the same time read the data, and then one of the users was very fast, and they did the transaction, and basically they withdraw some money, and that amount was reduced from the balance. So let's say the balance was 200, and they withdraw 100, so the balance is 100, and we store 100 back to the database. So if you look at the transaction table for that account, let's say 234, the balance is 100. While that other user, they read 200, and basically they withdraw, let's say, 50. So the balance is 150. So when we save, what will be the balance saved? It will be 150. So basically, this will create inconsistencies. The 150 will override the 100, and in this scenario, we have an inconsistent state. Inconsistent means the state of the database does not reflect the reality. It does not keep everybody with a happy face. So in this scenario, what was the balance supposed to be? Supposed to be 100 minus the 50 the other guy withdrawn. The balance should have been 50, not 150. Okay? So this is an example of anomaly that will happen if there is no concurrency control. Like one transaction comes along, and another one transaction, they start at the same time, they read the same input, and one of them did some change to that particular data item, and they committed that change. And then the other transaction did a change to that data item, and then it came and overridden the change that T1 has done. And basically, the change that T1 has done is lost. That is an example of anomaly. The other one is another example of anomaly, if there is no concurrency control, is the dirty read, if you remember. The dirty read. What is the dirty read scenario? An example scenario of a dirty read. So we have transaction T1 trying, let's say, to update a particular table. Let's say, let me give you a small scenario. I'm going to take all employee table and basically increase the salaries by 10%, provided that the total salary will not be more than, let's say, 1 million. If it's more than 1 million, I will roll back. Okay? So I did an update. So T1 started doing an update to the employee table, increasing the salary to salary times 1.1 to increase it by 10%. And T2 came along, and basically while T1 is updating, let's say it's finished updating employee 1, 2, 3, and their salary, let's say, was 2,000, and now it is 2,200. And then T2 came along. It tries to read the salary of employee 1, 2, 3. So if there is no concurrency control, they will read 2,200. So the T2 will read the salary of 2,200, while T1 is still doing the work, and it will do its validation at the end. It says, oh, I tried to do salary increase, but this will go beyond the allocated budget, so I will undo it. So the T1 decided to roll back, which means all the changes will be undone. We will undo them, while T2 read something that was not committed. It was kind of in progress. This is called the dirty read. So it might take that value and maybe act on it, maybe issue a payment check or put it in the statement, in a salary statement or like a work statement, and suddenly the employee will receive it that their salary has increased. When the payday comes, they will be surprised that there is no increase. This is an example of inconsistency, the dirty read. So for these reasons, database management systems need to invest in mechanisms to allow these concurrent transactions to execute, but without having these unwanted side effects or unwanted anomalies like lost update and dirty reads. So that's basically the goal. The goal is that we don't want to go back to single user database. That's not an option, because single user means the other users have to wait. The performance and the throughput will be very, very slow, and everybody will be waiting one at a time. That's not an option. So we want to have concurrent executions and without anomalies. So that's why we need concurrency control mechanisms. Okay? So, and if we have a proper concurrency control mechanism, we can achieve higher throughput. Higher throughput means we can execute many transactions in a particular unit of time, and also without corrupting the database and without losing consistency. All right? Now, first of all, before we go into the mechanisms, I last time kind of tried to explain a very important property. If we have multiple concurrent transactions, this is an example, T1, T2, and T3. So this schedule, this is called a schedule. A schedule is basically multiple concurrent transactions issuing read-and-write operations. So database, at the end of the day, that's what it sees from the outside world. It sees transactions coming in, and these transactions are requesting a read and a write. Okay? Now, transactions that are reading and writing different data items, there is no problem whatsoever. If we have many drivers, one is driving Shamal Road, the other one in Corniche, the other one in Airport Road, do we have problem? We have no problem whatsoever. There is no concurrency problem in this case. Multiple users using the same database, but everyone is doing different things. Do we have a concurrency problem? No. When do we have concurrency problems? Yes, when they are trying to read, or more particularly, when they are trying to write same data item. Then we have concurrency problem. Okay? So first of all, if we take transactions that are coming in and we queue them and we execute one after the other we call this a serial execution or a serial schedule. One transaction, when it's finished, we move to the next one. When it's finished, we move to the next one. This we will have zero concurrency control. We will have zero concurrency problems. But of course, the throughput and the response time will be lower. People have to wait a long time on the queues. So here, what I want to say is we can allow interleaving, we can allow concurrent executions as long as the schedule has a property called serializable schedule, as long as the schedule is serializable. Now I'll give you the concept first, and then we will see the mechanisms how database enforces this serializability. So a serializable schedule is a schedule that can run, and it will leave the database after completion as if it was a serial schedule. Can you see the terminology? Serial means one after the other. Serializable means they are running concurrently, but the end result is as if they have run, they will run concurrently, but the end result is as if they have they have run in a serial fashion. Okay, so to verify, just to show you this property, like to show you that some schedules can be serializable, others are not serializable. So first let us understand this concept and theoretically, and then we go into the mechanisms to achieve it. Okay, so this is an example schedule. So we need some kind of a formal way, some kind of technique to determine or to decide whether the schedule is serializable or not serializable. So to do this, we create what is known as a precedence graph. A very simple graph, you can draw it. The way you draw this graph, you have nodes. What are the nodes? The transactions. How many transactions we have that are running concurrently? 3. So we have T1 and T2 and T3. Yes? Then what we do, we take one transaction at a time. One transaction at a time. By the way, database will not do this in real life. This is just to understand this property of serializability. Okay? So there are mechanisms database uses to make all schedules serializable. But before we go to the mechanism, you have to understand this concept of serializability. Okay. So now, for us to understand it, let's draw this precedence graph, which is made up of nodes, and we will draw the edges. Okay. So the nodes are basically our transactions, and the edges, the way we draw the edges is we take each transaction and we look at a potentially conflicting transaction that comes after our operation. So what I mean here, is there any conflict, a potential conflict between a read A and read B? No, they are reading different things, no problem. Any conflict between read A and write B? No conflict. So I look at the ones that come after. Okay. Now, is there any issue with the read A and the read A? No problem. If we are reading the same thing at the same time, there is no issue whatsoever. Okay. Now, is there any potential conflict with the read A and the write A? Yes. The read conflicts with the write. Okay. So I have to read first. I cannot swap. Can I swap those? Can I let this go first before this? No problem, because a read, I can swap them. But in here, can I swap? Can I let this go first and then do the read? I cannot do that, because I might be reading different value if I read after write. So what I mean here, these are conflicting operations that cannot be swapped. I cannot do this first, then come to this. Remember, concurrency control is all about for the scheduler to say which transaction should go first. Okay, so for it to decide which transaction should go first, it has to analyze these potential conflicts. So in here, definitely T1 must go first before T3. So basically, when there is a conflicting operation, I draw an edge, and I can say basically this is the conflicting operation, conflicting on A. So there is potential conflict. If I allow A to go first, then basically what I want to say here, I cannot swap these. So there is some precedence. There is some precedence between these transactions. So in here, what I'm saying is T1 must go first, then T2, because I must read before T3. Sorry. Yes, you're right. So let me just. Yes, you're right. T3. T2, there is no precedence between them because they are reading and writing different operations. Okay, did I finish? So I finished with this. Right A. Let's go with the right A. So right A, is there any potential conflict with T2? No, because they are reading and writing different items. Now, write A and read A. Yes, there is potential conflict. So read A has to be after we write. So I already have this precedence that T1 must go first before T3. So I don't need to draw it again. It's already there. Now, write A, of course, there's conflict. This has to go first, and then this comes later. Okay. Now, I finished. Did I finish? Yes, I finished with these. Now here, is there anything that came after this? There's nothing. So T1, I am finished with T1. So I looked at other transactions. I looked at operations that came after the operations of transaction I'm studying. And if there is a conflicting operation, conflicting means read with write, or write with read, or write with write. Read with read, no problem. Or if they are reading or writing different data item, no problem. Okay? So we finished with T1. Yes? Now let's go with T2. T2 here, is there anything after read that conflicts with this? So we have a read B, no problem. A read B, write B is a problem. So there is a precedence between T2 and T1. Between T2 and T1, there is a precedence on B. I don't need to write these if I don't want to, as long as I know now that I will have a problem if I allow T1 to go first. T2 should go first. Okay? So this one, halas. Here I finished with this. With T3, I go here, write B, read B. Of course, there is a conflict. So I already have this arrow here. I don't need to draw it again. Write B with write B. Of course, there is a conflict. Now T2 and T3, nothing comes from T3 after T2 operations. So there is no issue. Now let's take it from here. Read A. Is there anything that came after these operations in T2 that's conflicting with read A? Read A, read B, no problem. Read A, write B, no problem. Read A, write B, read B, no problem. No problem. These are no problem because they are basically they are dealing with different data items. There's no issue. So the precedence graph, as long it does not have a cycle, it is an acyclic graph. Acyclic means there is no like T1 saying, oh, I must go first, and T2 is saying, I must also go first. And basically there is kind of their like arrows pointing to each other. In this case, there is a cycle, and that schedule is called non-serializable. But this schedule is a serializable schedule. Serializable. Serializable schedule, which means have a look how the database will really execute it. What happens is this serializability is achieved by database using a lock-in mechanism. So using a lock-in, not just lock-in along with the protocol. So I'll explain what that protocol is. But just have a look what will happen. According to this lock-in protocol, let me just tell you the lock-in protocol. It's called two-phase lock-in protocol. So for the database concurrency control manager to achieve serializability, it does not go through this graph. It can, of course, but that's another approach that I will discuss. But first, I want to give you the realistic way, or the real way in most databases how serializability is achieved. Serializability is achieved through lock-in. Exactly the same analogy as like crashes are reduced or hopefully eliminated in shared roads and shared intersections through red lights. Okay, and red lights, they are not just physical items. They have kind of a policy or a protocol associated with them. So the protocol says when it's red, stop. When it's yellow, if you are already past, continue, otherwise you should prepare yourself to stop. And when it's, let's say when it's flashing, means it's kind of disabled, you are on your own. Like, apply the other rules. You fall into another protocol. The ones who has the priority, the ones on your left side have the priority. You see here, there is a protocol. What is the goal of this protocol? Is to avoid these collisions. Is to basically to avoid the anomalies of you concurrently using the same roles. So the same thing here. So for the concurrency control manager to allow this concurrent usage, concurrent reading and writing of same data items without anomalies, it needs to follow a lock-in protocol. So it uses a lock-in mechanism following certain protocol. So let me take this example, and we apply the protocol to show you how that protocol achieves serializability. Okay? So here it is. So the protocol says, before you read any item, before you read any data item, you must acquire a shared lock. Is clear? Before you read any data item, what should you do? You should ask for a shared lock. Shared lock means I'm asking the concurrency controller, please give me the shared lock to enable me to read that particular item. Now the concurrency control will say, oh, if somebody else has a shared lock, will the concurrency control give you a shared lock? Oh yes, it's called shared. If somebody is also reading the same item, concurrency control will be very happy to give you the shared lock because you are only reading. Yes, shared for reading and exclusive is for writing. So let's say I hold a shared lock on A, and somebody asks for exclusive lock on A. Will the concurrency control manager give it? No, it will say wait. It will not say no. It will say wait until there is no shared lock or there is no lock on this data item. Then I will give you the permission. So the lock is kind of a permission that allows you to access a particular data item. So let's go like this. So T1 is the lucky one, just came in first, and it says, I want to read A. It asks for a shared lock on A, and the shared lock is granted. So basically, there is, let's say, lock S. So let's see what T1 is doing. So this is what T1 is doing. it will say lock, shared lock on A. This one will be granted. Yes. And that shared lock will allow A to do read A. No problem. This will be fine. Okay. Now write A. See here, T1 is trying to do write A. What should it do first before it can write to A? Request an exclusive lock. Or in this case, because it already has a shared lock, it will ask for upgrade from shared to exclusive. So here, when the concurrency controller receives an exclusive lock, it will look, is there anyone has a lock on this item? Either it's shared or exclusive, the exclusive will be denied. Exclusive, as the name suggests, one transaction has that lock at a time. So for writing, one transaction at a time can write. Okay? And the concept of locking, you're already familiar with it. We all have come across trying to delete a file in Windows, and you cannot delete it. It says this file is locked because some other process is using it. Okay? So the only option, you try to find out that process, or you have to restart the machine, or log off, or do something to kill all the processes. Same thing here. That file has, that particular process, because it is a write-in, it has an exclusive lock. You cannot, for reading it's fine. You can open it, multiple applications open the same file, there is no problem. But for writing, one at a time. Same concept. So it will ask for an exclusive lock on A, lock, I will call it here X on A. This will be granted because no one has any lock on this yet. And then it will do a write A. Yeah. Now, very good point. Maybe you are okay. Because it is the same transaction, you can ask for upgrade, no problem. Because it is the same transaction. Same transaction, you can ask for an upgrade. No problem. It will be granted to you as long as other transactions do not hold the shared lock on exclusive lock already. If they already hold the shared lock, other transactions, then you have to wait. Okay? Now, this is T1, and then T2. While T1 is doing this, T2 came into the picture. Can you see it? T2 came along. First of all, what was the sorry? What did we decide? What was the graph? This is T1, T3, and T2. Yes, I think it was like this. Yes. Okay. Anyway. So let's see. Read, no, T3. Let's start with T3. Let's start with T3. Okay, so because this is the kind of the time of arrival. This is kind of the time, go in, and this is the time of arrival of the operations. Now T3 is asking to read A. Remember, this transaction is still going. It did not commit yet. I did here, let's say, begin transaction. I have not committed yet, which means the transaction still hold on onto the locks. Now, T3 came along, want to read A. What T3 should do before it read A? It asks for a shared lock. It will ask, please give me a shared lock on A. What the concurrency manager will say? Wait. It will not say denied, it will say wait. Okay? It will say to it, please wait. Yes? So this guy cannot do anything. They are waiting on the queue for the lock on A to be released. So while T3 is waiting, T2 came along. See, T2 came along. Here is T2. And then, before T2 can do anything, what should it do? It should ask for shared lock. So it will ask for a lock, shared lock on B. No one is using it. So T2 will get the lock, and it will be able to read B. Yes? Is able to read B, no problem. And then it basically wants to write B, change it, update that record. So it will need to ask for upgrade. In this case, it already has a shared. It will ask for upgrading to exclusive. So it will ask for an exclusive lock on B. This will be granted because the shared lock is held by the same transaction, no problem. So it will be granted, and then this guy will be able to read B. Sorry, write B, no problem. Okay. Of course, this one is still going. Now, T3 cannot do anything. It has to wait. Okay. Now, here it is, T1. T1 tries to read B. What it needs to do? It has to ask for an exclusive lock, a shared lock on B. Will this shared lock be granted? No. What TA1 should do? Wait. Can you see it? Now, for us to move forward, what should happen? This one should commit. Once this one commits, commits means it made the changes permanent. And that's it. I am 100% sure there is no abort, there is nothing. And the reason why it's locking, because it is protecting this guy from dirty read. That's why they have to wait. If they didn't wait, they might end up with dirty read if T2 decided to abort. So to be on the safe side, T1 has to wait until T2 commits. Now T2 commits, this can go along. As soon as this one commits, the lock will be released, and this will be from waiting to granted, and it can continue. Yes, please. No, it's exclusive. For reading here? No, here it's lock. It's asking for a shared lock on B, but B is exclusively locked by T2, so the shared lock will not be granted. Okay, so that is the idea. So basically, shared, if there is already shared, it will be granted, no problem. But if you ask for a shared lock and there is an exclusive lock on the item you asked for, you will have to wait. Because exclusive is so selfish, it doesn't allow anybody with it. It has to finish, then it can make it available to others. Yes, on that particular item. This item could be, let's say, a row on a database, or a range of rows on a database, for example. Okay, so it has to wait. And if you remember, I showed you during the demos we saw as an introduction to this lecture. If you remember, we tried to update two windows to represent two transactions. We were updating, let's say, employees, increasing their salaries. When we go to the other window to try to read, while that transaction T1 did not commit yet, the other window was just spinning and waiting. Okay, so yes, please. No, T3 is now waiting for the TA to be released. for A, for the lock on A to be available. No, not yet. Remember, the protocol says the strict, particularly if we go with the protocol says the strict, it's called strict two-phase locking. When you get an exclusive lock, you keep it until you commit. Why is that? To avoid basically dirty read. So if you have an exclusive lock, you don't just let it go. Okay? So once T2 commits, then it will release the lock on B. T1 will get the lock, will be able to read B. So it will proceed with read B. And then it wants to write B. So it has to request for an exclusive lock on B. This will be granted because the shared lock is owned by the same transaction. This will be granted, and then it will be able to write B. And hopefully this transaction is done. It will do commit. Either way, either it does a commit or rollback, as long as it makes up its mind. It's not like still hanging on things and still deciding. So once it commits, that's it. The locks will be released. So the locks will be released. So the reason why we don't release the lock when we're done with it, because the protocol says once you release a lock, you cannot ask for more. You have to release all what you have. That's why it's called two-phase locking. There is one phase, it's called the growing phase, where you just acquire as many locks as you need. And there is the shrinking phase. That's why it's called two-phase locking protocol. The shrinking phase, once you start releasing, you cannot ask for more locks. That's it. You took your chance. You get all the locks, you use them. Once you release one or downgrade one from exclusive to shared, you are done. You cannot ask for other locks. That's what this protocol means. Okay, so this one committed, and now this one will have the privilege to do so. So instead of waiting, the lock manager or the concurrency control manager will grant this lock to T3. It will be able to do its read A, and then it will ask for exclusive lock on A. This will be granted, and it will be able to do write A. And hopefully it will commit or abort. It doesn't matter. It's up to it. Khalas. You see here, this schedule is serializable schedule as long as T2 has to go first, followed by T1, followed by T3. Otherwise, this will not be a serializable schedule. If we do it this way, using this protocol, we can get this transaction to run concurrently. Running here concurrently means they do some work and they have to wait for others. We are using rows concurrently. It doesn't mean we have the full freedom. I want to take another road, I just like turn to the other road and go. It does not, when we say we have the freedom to use the roads, it doesn't mean you can do whatever you please, okay? There are some protocols, some rules you need to follow, and sometimes you have to wait until you get your chance. Same thing here. Sometimes transactions, although they came first, you still have to wait until the road is clear, and then you proceed. No, for shared lock we don't wait. Where did we? Here we waited for a shared lock because this one has an exclusive lock on it. Of course, look, exclusive means somebody is trying to write to that data item. So while it's writing to it, reading is not allowed. Why is the reading is not allowed while writing is going on? Sorry? Yes, the risk of dirty read. Because if this one was allowed to go ahead, what will happen is this might change its mind and roll back. And suddenly, this guy is ending up with a dirty read. You get the idea? Okay. So basically, concurrent transactions are allowed to interleave, to have execute concurrently, as long as the schedule is serializable. Okay. Now, the database. What the database they do? There are two approaches to enforce this serializability. Serializability means the transactions will run, and the database state will be exactly the same as if we run them serially, one after the other. That's what serializability means. Now, there are two major techniques database uses. There are one family of technique, we call them pessimistic techniques. And another group or category of techniques, we call them optimistic techniques. Okay? Now, most databases use pessimistic techniques, such as the lock-in. Lock-in, it has a pessimistic view. It says there will be conflicts. Let's not even allow a room for this conflict to happen. Okay? Basically, let's avoid the problem from the start by doing this lock-in protocol. So this is a pessimistic approach. The optimistic one, it says, oh, the conflicts are not that common, very infrequent. Let's not enforce any, do any check-in or enforce any protocol during the execution. Okay, let every transaction do what it pleases, no lock-in, nothing. But before we commit, we do a check. We do a check with concurrent transactions. If there are conflicts, then we abort. We roll back. So this is pessimistic. It assumes there will be conflicts, and the conflict is the rule. So in this case, let's avoid them from the start. Let's not allow them to be there in the first place. So it uses mainly lock-in techniques to achieve this. Optimistic says, let every transaction have the freedom to do whatever it pleases, but I will catch them when they come to commit. When they come to commit, I will do my analysis, maybe my graph or some other, my precedence graph or some other analysis. And if I find a conflict, I will not allow that transaction to go ahead. I will force it to abort. So these are the two major family of techniques. So, and the most common one in real implementations in most databases is a lock-in based mechanism. It works very well. The other one, a lot of work around it, but practically it's not that common. All right, that's basically the precedence graph. All right, now here is another example. We did it last time, if you remember. And here, when we draw the precedence graph, we came up with the graph like this. And you can see here, the graph is cyclic. There is a cycle. Here, T1 says, I have to go before you, and T2 says, I have to go before T1. And the schedule will say, none of you will go. This is a non-serializable schedule. This schedule will not be able to run with that causing conflict. So one of the transactions will be aborted to allow this to happen. Okay. Same thing here. This one is a non-serializable schedule, and you can see that this one is an example of lost update. You see these guys, they both of them read, and one of them goes ahead, changes what it read, and goes ahead and update. And then this one goes ahead and update, and of course this update will override this one. So if you allow this schedule to go ahead, what will happen? A loss update. So this will not be allowed. And the lock-in will not allow this to happen. If we use a lock-in mechanism, this will not happen. So, for example, in here, let's try to see how we can use the lock-in. So we read here, and then we read n, and then we try to change it. Okay, and then we ask for exclusive lock. We ask for exclusive lock on n. Okay, we ask for exclusive lock on n, and this one already has an exclusive lock. Sorry, shared lock. So this exclusive lock will not be granted. Okay, so this will not work, even using this strict two-phase protocol, because it will result in a loss update. So for this to work, this guy has to lock this one. Okay, let me see. One of them has to go first. Let me see. Yes, please. Okay, so let's see. Let me see. So here, yes, this is how it will work. By acquiring the needed lock up front to prevent T2 from reading in the first place. So in here, read, like basically ask for a shared lock, an exclusive lock on n, immediately at the start of T1. So when T2 comes, it will be denied a read. It has to wait for T1 to proceed first. That's the only way. The only way for this to happen without loss update is that T1 should exclusively lock n at the start of the transaction, which means in this scenario, you acquire all the resources up front. You require them up front. You know what you will be doing with your resources. Acquire them up front so you don't have competition from other transactions. If future transactions come, they have to wait. They have to wait for you. Otherwise, you will end up with this loss update. Yes? Okay, if we start from T2, so if we just use this strict two-phase commit, it will still. So if we just so this one has shared lock. This one has shared lock. Okay. So and let's say this guy updates this, and this updates n. Now, shared lock is still held by T1, yes? And basically, here, T2 is trying to acquire an exclusive lock on n. So it has to wait, yes? And this guy is also asking for an exclusive lock on n. It has to wait. So T1 will be waiting for T2, and T2 will be waiting for T1. What do we call this scenario? The deadlock. So here, this will be prevented in all cases, even if with this protocol. We can try it. Shared lock on n, yes? Because it is shared, can this acquire shared lock? No problem. Now, they can change the value. They can change the value. Now, everyone is holding to the shared lock. You don't release until you commit or roll back. So we move on. This guy is asking for an exclusive lock. Will exclusive lock be granted? No. So T2 will be waiting for T1. And T1 to proceed, it's asking for exclusive lock on n. Basically, it has to wait because T1 has a shared lock. So T1, that's what the graph says. T1 is waiting for T2, and T2 is waiting for T1. What do we have in this scenario? A deadlock. Okay.
So even if people change the
No, it cannot be upgraded. Can the lock be upgraded here? When, yes, you're right. It tries to ask for upgrade. It says, I have shared lock. Please upgrade it for me to exclusive lock. What the concurrency control manager will say? Say, sorry, we cannot do that. Why? Why? Because T2 has a shared lock on N. So exclusive lock means it's fully empty. Okay? So if you want to cross a roundabout, there's nothing called shared entry in the roundabout. Exclusive, okay? Only one at a time. Otherwise, big problems. So that's the idea here. So exclusive lock, and because of this, you will end up with deadlock. Now, in a real life, in a real scenario, what's happened in these scenarios is that the engine, most of SQL, most of relational database engines, such as SQL Server that I'm familiar with, it runs some process in the background that periodically checks for deadlocks. It detects the deadlocks and it kills one of the transactions, aborts one of them. Now, which one it aborts depends. The one that has been waiting longer or the one that has done less work. So that's another decision the concurrency control manager has to make. Okay, but it's very easy to reproduce. In fact, before I came here, I tried to reproduce one just to show you an example, because this is quite funny, because you might come across this in real world. Let me just quickly. I think there are so many scripts out there to sorry, let me just okay. We'll just quickly go through this small example here from scratch. I will just create two tables. Here is, I will just close everything. Just to show you this scenario of deadlock and how it is handled in a real environment. So here I'm creating two tables. I will just change the names. Okay, sorry. We'll just delete them from here first. Delete. Okay, so what I have here, I have two tables. One is called table 1 and another one called table 2. It has basically two columns, ID and call, and there is a reference, a foreign key constraints between the two. So let me just change this to transdb. So call in table 2 is referring to ID in table 1. So I'm creating two tables. So let me just create them. So two tables are created. And let me start transaction. In first window, I will start a transaction trying to insert a record into table 1. I have not committed yet. I just created this, and then I'll go to another window. Another window means that I'll start another transaction there. So in here, I am going here and inserting into the second table. Have a look. See here the second table? I am inserting and in the second table, but referring to the ID that is inserted in the first transaction. So have a look. The first transaction is inserting a row with the ID 2, and the second transaction is inserting another row in table 2 and while referring to table 1. So let's run this. So this one is basically blocks and waiting. Can you see there? It's waiting because it is waiting to read, to establish the foreign key relationship. It needs to read from table 1 to make sure 2 exists in table 1. You know what referential integrity means, or foreign key means? Foreign key means anything I've put in the foreign key must exist in the primary table. Otherwise, I should abort. I should not accept the insert. So this is what this transaction is trying to do. But of course, it is locked by the T1 because the transaction in T1 is not committed yet. This is basically, it's asking for shared lock. It's not being given a shared lock because T1 has exclusive lock. Okay, so far no problem. But this guy will be waiting. As soon as the T1 commits, then this will be allowed to proceed. But the deadlock happens when we go to the other window. Okay, that's how this. I'm trying now to insert in T2. Have a look. I'm trying to insert in T2. So both of them are now waiting for each other. You see here, the SQL server detected this scenario that T1 is waiting for T2 and T2 is waiting for T1. It detected this scenario, and basically it selected one of them, this one. This T1 selected it and says, transaction 51 was deadlocked by another resource, on locked resource with another process and has been chosen as the deadlock victim. Rerun the transaction. The funny thing is that some developers, I have seen this in real life, you know when you do try and catch, and then they take the exception coming from the database and they show it to the users. And the users, they just pick up the phone to the help desk and say, I've been victim of deadlock. And so here we need to be careful. This has to be translated to something more meaningful to the end users. Yeah. No. Look, when a transaction begins, it's not committed until the developer explicitly issues a commit statement. So if it was committed, there is no problem. Once it commits, the other transaction can go ahead and get the shared lock. The whole idea here is that T1 is still going, and T2 want to make use of a resource that T1 has already access, in this case, exclusive lock to. It's asking only for shared lock, and it's denied for it. It has to wait. And then T1 came along and trying to get an exclusive lock, and T2 already have an exclusive lock. So T2 is waiting for T1 to get the lock on table 1, shared lock on table 1. And T1 is waiting on T2 to get an exclusive lock on table 2. And basically they are waiting for each other. This is a deadlock. So most servers, there are either deadlock prevention mechanisms or deadlock detection mechanisms. So most servers, they do deadlock detection. So they have some process that's running in the background all the time, and checking for transactions that are waiting for each other for for a certain period of time, and then they will choose one of them to be rolled back. Okay, that is basically the idea. So in here, like, database will not try to get all the so imagine the transactions are started and they are issuing commands. Database will not try to draw this stuff and say, oh, it makes a conclusion. There is no cycle, I will allow them. There is a cycle, I will not allow them. That's not how it works. So the way this serializability is achieved is through strict two-phase locking. You lock before you read, you acquire shared lock. If it's not granted to you because there is an exclusive lock already, you wait. Okay, and then if you want to write, you ask for an exclusive lock. If another transaction has either shared or exclusive, you cannot get it. You have to wait. Okay, and then basically another rule in the protocol, you can ask for locks, but once you start releasing, you can no longer ask for locks. You have to release what you have at your hand. So if you follow this, of course there are proofs that this will always result in a serializable schedule. We can face, yes, you're right. We can face deadlock with this. Now, to avoid the deadlock, remember there is always like a trade-off between concurrency and consistency. There is a trade-off between concurrency and consistency. Now, in here, if you look here, what I'm doing, I am asking for locks as I go. I'm not asking for all the locks up front. If I ask for all the locks up front, there will be no deadlocks, but the concurrency will be reduced. So, for example, as I explained here, for us to avoid this deadlock, the only way to do it is the transaction up front. It acquires all the locks requires and then starts, which means in here it says, oh, I will need n not only for reading but also for writing. So it will acquire from the start of the transaction an exclusive lock. So in this case, n will be exclusive to T1. When T2 comes along, what happened to T2? I must wait. And then there will be a deadlock? No deadlock. But the concurrency and the throughput will be reduced. T2 will have to wait. T2 will have to wait means the user that issues that command will have to wait for the answer to come from the database. So the response time and the throughput, which is the number of transactions executed per unit of time, will be reduced. But the consistency will be increased, and the deadlocks will be avoided. So in most scenarios, the strict two-phase lock-in is enough. But again, since we already started this, in the database, you can control the level of lock-in, the mechanism of lock-in. It's not a switch. It's not switch on or off. The lock-in mechanism is a dial. You can adjust it the way you wish. Okay? So since you already asked this, so just for us to connect this is a very important question. If you really want to control, you can think of this as kind of the default protocol. The default protocol is I acquire the locks as I need them. Okay? If I ask for exclusive, if somebody already has it, I have to wait. And then basically once I start releasing, I will no longer acquire any new locks. Now, the other, if I want to be more strict, I can acquire all the locks up front, and then this way I can avoid this deadlock scenario. Okay. Now, for you as a developer to control the way lock-in is really done, the database has what is known as isolation levels. Isolation levels. So, before you issue your statements, you ask the database, please use isolation. There are at least 4 isolation levels that are very common. There is something called read committed, repeatable read, and serializable. Serializable is the most rigid or the most rigorous isolation level available. So maybe I'll delay that discussion until we go into a little bit more details, but just be mindful that as developer, you can control the level of serialization if you wish. Okay. Okay, this is just to summarize. I hope it's a bit clearer. Okay. So in terms of mechanisms to achieve serializability, we need to use a concurrency control protocol. There are so many concurrency protocols out there, and it's an area of research and development. One of the areas people always invent new protocols. But the most common used ones, a 2-phase lock-in protocol, a timestamp ordering protocol. These two are pessimistic techniques. Pessimistic means they do interventions while the transaction is running to try to prevent the concurrency problem in the first place. While optimistic, as I explained, they let transactions do what they please, and then just before they commit, they do the validation. There's a validation phase. If a transaction happens to be in violation of the concurrency rules, then it will be aborted. Okay. So we will see some of these, but we will focus more on the lock-in. Okay, so let's start with a lock-based concurrency control, which I mostly explained here. I just go through it quickly if there is things that are not well explained. Okay. So locks are ways of achieving serializability. Serializability, I explained it, and I explained how we establish it theoretically using the precedence graph. Theoretically, or if you want to go with optimistic concurrency control, then precedence graph can be very, very useful. But for precedence graph, you have the whole operation. You have to wait until the end to draw the full graph. Then if there is a cycle, you can go back and basically roll back the transactions that have a cycle. Okay. So for locks, there is a lock manager that grants locks. So transactions, before they read or write, they ask for locks, and then the lock manager will grant the locks. So the readers block writers, and the writers block readers. That's the idea. So readers, if I have a shared lock, let's say here, I have a shared lock. Where is it? Okay. Lock S. Lock S. Which one? I have a shared lock. Yes. So for example, I have shared lock on A. This T2 cannot ask for exclusive lock. It can ask for shared lock, no problem, but it cannot ask for exclusive lock. So the readers, they block the writers. And the writers, they block the readers. So if I have, here I have exclusive lock on B, no other transaction can get a shared lock on B until I release it. So that's the intuition. If somebody is reading some item, nobody can write to it. If somebody is writing an item, nobody can even read it until that transaction has finished the writing. Okay. So here is the state diagram of the locking mechanism that I explained already. So here is the request. A transaction requests access or requests a lock. So if the lock is available, the transaction will get the lock and it will go and immediately access the data item. Now, if the transaction is not, sorry, if the lock is not available, so the transaction goes into a queue and wait. Once the lock becomes available, it will get the lock and access the data item. So that's the state diagram of transactions with respect to locks. Okay. So this is the idea of shared lock. Two transactions acquiring shared lock, there is no problem. Multiple transactions are reading the same data item, no problem. But one transaction is a reading, sorry, one transaction is a writing, other transactions should not read. Otherwise, they might end up with lost update. That's why we have the exclusive lock mechanism. Okay, so here is the red lock state diagram. So the red lock, if somebody is asking for a red lock and the lock is available, they will be granted that red lock. As long as there is no exclusive lock, they will be granted the read lock. Now, if there is an exclusive lock, then the lock. So if transaction gets a write lock, then the shared lock will not be available until TX finishes with the writing, and then the lock will become available. All it means is exclusive lock will prevent others from reading the item that is being exclusively locked. That's what this diagram is trying to say. Now, for the write lock, a write lock, as soon as a transaction, it could be multiple, as soon as any transaction acquires a read or write lock, then that write lock will become unavailable until there are no more shared locks and no exclusive lock on that item. Then the exclusive lock becomes available. So, which means that exclusive lock, only one transaction can have it at a time. If others have a shared lock or one of the transactions has an exclusive lock, then the requester has to wait. So this is summarized here nicely. So read lock with a read lock, no problem. The rest, they have to wait. These are incompatible. Read with a write with a read, a write with a write, incompatible. Only reading, locks for reading, multiple transactions can have the same shared lock, no issues. Okay, so locking is a mechanism, but by itself is not enough to achieve serializability. So for us to achieve serializability, we have to follow a protocol. And the protocol, the most common protocol is the two-phase lock-in protocol. It has different flavors. The most common one is this one, a strict two-phase lock-in protocol. This protocol says a transaction must hold all its locks, all its exclusive lock until it commits or aborts. So once you get an exclusive lock, don't get rid of it as soon as you finish with it. Keep it until the end. That's the idea. Because if you let it go, other transactions might start acquiring shared lock and reading, and then you might abort and they end up with a dirty read. So that's why you have to follow the strict two-phase lock-in protocol. Now, as I explained, the two-phase lock-in means there are two phases. The growing phase, transaction can ask for locks as it needs. And then once it starts unlocking, it cannot request more locks. So there's the growing phase, and then the shrinking phase. And following this will give you serializability, as we've seen through this example. This is just a kind of a diagram where this is the number of locks acquired by the transaction. It keeps on growing. And then once it starts unlocking, it has to go and unlock the remaining. It can no longer ask for more locks. There's no like up, down, up, down. There is up and then down. Now the strict two phase, there is up and then one down, which means you keep the locks until the end and you release them after the commit. So, okay. Now this is the strict. There are various versions, and each one addresses some of the limitations. So each kind of flavor of the two-phase commit addresses some of the limitations that I didn't go through a lot of details. But here is the most common two-phase locking protocol that most databases use, which is the strict two-phase locking. The strict two-phase locking says, hold on to your exclusive lock until you commit. That's what the strict two-phase locking says. The rigorous two-phase locking, which is even more strict than the strict, it says hold on to even your shared locks until you commit. Okay, so each one has its own advantages. The more you go strict, the more your concurrency goes down. And of course, the less problems you have, less concurrency problems you have. Okay, so this one I already explained through the example. Before you read, ask for shared lock. If it's available, you will be lucky to get it. You go and read. If it's not available, you wait. That's basically the idea. You keep acquiring locks. Once you start unlocking, khalas, you cannot ask for more locks. That's the protocol in more details. Okay, deadlocks, we also explained it. Deadlocks is when we have T1 waiting for a lock to be released, for a lock held by T2 to be released, and T2 is waiting for T1 for a lock held by T1 to be released. And two transactions waiting for each other. And basically, we have a deadlock situation. So there are we have two techniques to solve the deadlock. There is the detection techniques and there is prevention techniques. Now detection, this is what most databases use. In the background, some process runs, and if it detects deadlock, it will choose one of the transactions to be aborted. The prevention technique, as I explained, the only way to prevent deadlocks, acquire all the locks at the start before you do anything. And for example, here T1 has intention to update A. In the beginning, ask for exclusive lock from the start and hold on to it until the end. Then there will be no deadlocks because anybody coming after you will have to wait. So there will be no deadlocks. You block them. So there's no problem. You will not need to wait for them because they are waiting for you from the start. But of course, the concurrency will be reduced. So most databases, they choose to go to the detection mechanism rather than prevention mechanism to improve concurrency. And now, in terms of which victim transaction to go with to kind of kill, is either you abort the oldest, the one that has been going along for a long time, or you abort the one, the most complex. Okay, give a chance to the ones that just doing small things. Let them go quickly, and then leave the room to the big one to take its time. I already explained this. Now, in terms of practical, when you, as a developer, you should be careful here not to always get the exception from the server and then display to the users, because it might not be very meaningful, like this one. This is a real scenario. So handling deadlocks, that's what I explained. Another way to handle deadlocks is by using timeouts. So this is an area of research and development. People always come up with the new novel ideas to handle deadlocks. Another idea is to have timeout. So when you have a lock, when you are holding a lock on a particular item, a timer starts. So you have, let's say 20 milliseconds. During that 20 milliseconds, everybody has to wait for you. After the 20 milliseconds, that transaction, that lock becomes vulnerable, which means if somebody asks for it, that transaction will be aborted. Okay, that's the idea of timeout. But the challenge here is how long what is this optimal timeout that we put? That is the challenge. So it's very hard to decide an appropriate length for this timeout. So let us just take maybe 10 minutes break, and inshallah when we come back I will explain this transaction isolation levels. This transaction isolation level more practical. In practice, as developers, as a database developer or administrator, you should be familiar with those because that's what developers will use. But you will be able to understand them better because you are equipped now with some kind of prerequisite knowledge that will make it hopefully easier for you to understand. But this part here is really practical, as I will show you after the break. All right, thank you.